Alright, so as y'all connect, go ahead and put something into chat so I can know about how many people are here. How's it going? Good. Looks like we have already 10 people. That's great. Or 7. It's changing. Again, if you get into the stream, make sure you go ahead and put something in chat so I know who's here. There's also going to be a little bit of a delay from when y'all type it in versus when I see it. Maybe 5 seconds or so. So please bear with me. Steven, good to see you. Or not see you. Good to meet you. Gatsby. How are y'all doing? Cable, how's it going? Felix, good to meet you. Hello, Sylvia. Hope you're doing well. Did you take an algebra class with me, Sylvia? see. I think we're supposed to have a decent number of people in the class. 1, 2, 3, 6, 17 people. Okay, it's about 11:08, so I think we'll go ahead and get started. And then everyone else can catch up. Um, this is Calculus 2. I hope you're all doing well and have been getting through the first classes pretty well this week. I'm Joseph Severino, for those of you that don't know me. I've been teaching them in the college since 2002, and I frequently teach Calculus 2 once or twice a year, basically every year. So it is something I have a lot of experience teaching and I really enjoy. I also teach the differential equations class in the spring, which if you do continue beyond Calculus 2, that might be the next class that you'll take. You can actually take differential equations in the spring and then do Calculus 3 in the summer if you like, or Calculus 3 in the fall if you're still going to be around in the fall next year. So anyway, that's further down the road. Let's worry about Calculus 2 first. So yeah, it's going to be a little bit different this semester being online, but we'll get it figured out to some extent. So let's go ahead and look at the syllabus and some of the things that are some of the details about the course now. So I've got all these in files in Canvas. Starting off with the addendum that I made to the syllabus. So this is Calculus 2 IVC. That's an interactive virtual class. So we do hope to make this interactive to a certain extent. If you do have questions, make sure you type them in the chat. And then occasionally I'll ask you questions that, and I'll look for you all to respond in the chat accordingly. So hopefully I have some level of interaction here. It's not just me lecturing. As I want, and I mean, we can go through it with just me lecturing, but if you do have questions, I want you to, if there's something that you're kind of stuck on, definitely let me know so we can hit that before we move even further beyond that. And again, sometimes I will ask questions and see. This will help me gauge where the class is at as far as the knowledge of what we need for this course, both before and current. So definitely want to participate. You have my phone number here. I'm not actually in my office this semester. However, the phone number, you can call and leave a message for me, leave voicemail, and that'll be sent to my email box, and that way I can still listen to it. Or if you prefer, you can just send me an email or even message me through Canvas. At least with Canvas, I have it set up to notify me on my phone, so that might be the easiest way and the quickest way to get a response there. I can't guarantee that I'll look at it if I'm not, in my office hours period, but I will probably see it at least, and if it's urgent, I'll reply. Or if it's short, I'll definitely reply. If you have any questions, like as we go through this semester on homework, you can send me something through Canvas, and either I can point you in the right direction, or in some cases, if it's kind of a more complicated question or requires a more thorough explanation, I can create some different videos for that and post them on Twitch and then YouTube later. That way you can I can go through the problem in detail and give a thorough explanation about why we're doing what we do to solve this particular question, and hopefully that will be a helpful thing. So, here's my office hours. And again, that's set up by day. So anytime during those periods, you can expect me to respond very quickly to any messages you send me. Outside of those periods, I'll may or may not look at it, especially if it's night. So, but yeah, definitely if you have questions, let's just stay in contact so we can get things figured out. So, we're going to have 4 exams during the semester, 4 chapter exams. We basically cover 4 chapters, so I guess you can kind of see where that's going. I may cut that down to 3. I don't know. Chapter the last chapter we have, I think chapter 10. Depends where we are at the end of the semester. I guess that's probably what it amounts to. Anyway, however many tests we have, 3 or 4, they'll be equally weighted, and those will just be set up as tests in Canvas. And what I'll probably do is for each question have you submit a scan or a picture of your work. That way I can look at how you're progressing as far as how you work out the problem and apply the things that we've been learning. So, and then the final exam, you should anticipate this being a proctored final exam. And what that means is you could take it in person. You don't have to. You could take it in person, or you could set up to take it through a video call. You will need a webcam for that, or something of that sort. So that may be a little bit more challenging, but we should anticipate that being proctored, and we'll probably talk about that more once we get into November and closer to the end of the semester. But just letting y'all know now that it's something you should anticipate happening this semester. So basically, we want to make sure that it's you that's taking the final, and make sure that you're adhering to the standards that we set for taking the final exam. So you should expect to have like an ID, either your college ID or your driver's license works, just to prove it's you, and also that you're correctly taking the exam, that kind of thing. So anyway, the chapter exams will equally weighted. That's 70% of our grade. Final exam 20%. I don't know why this is at a different font. Oh well. Now I will assign homework from the textbook, and you're certainly encouraged to complete these between classes. I'm not going to pick it up for a grade, but again, you have to be responsible to keep up with that and stay current in the course, and that's part of the challenge. And certainly if you have questions, I can go over whatever we need to go over. And I can, if you have questions, I can still, at the beginning of each class, work on a few homework problems, show how those are worked out, and before we move on to the actual lecture, because I think we'll have plenty of time to do all that. So, at the beginning of class, if you do have questions, make sure you let me know. I'll probably ask for them at the beginning of each class, and then we can go from there. For the other part of our grade, I mentioned the exams and the final. That's 90%. The other part is on these computer projects with Matlab. Now, because this is an online class, we don't really have access to Matlab. So I'm thinking we can use what was actually the open source alternative to Matlab, which is I believe it's called Octave. Anyway, hoping that's going to work, but if it ends up not working, I did add a kind of a caveat there in the syllabus that the projects will count 10% unless we don't end up doing the projects, in which case that will be split equally between the chapter exam and the final exam, meaning the chapter exams will be 75% and the final exam will be 25%. Okay. I hope we can do these, because one, it should be an easy grade, but two, I think it really helps us better prepare for the students that are moving forward, both in mathematics and in engineering. A program like Matlab or similar to that would be like Mathematica or Maple. It's a computer algebra system. Basically allows us to, it's actually its own programming language to an extent, but we're going to use it more as a kind of like a graphing calculator, but better, because it already has a lot of the functions built in, so we don't have to program to get to those functions, and that's what we'll focus on in this class. Most students in engineering and mathematics do end up using some kind of computer algebra system when they transfer as part of their major, and so that is something to expect, and what we want to do by offering or including this in our course is getting y'all better prepared to make that transition by introducing some of the basic concepts now, both in Calc 2 and Calc 3, and then also differential equations. But we haven't done this in IVT before. I'm hoping it works. As far as attendance and participation goes, just if you do have questions during lectures and you know you're watching live, or even if you're watching the recording of the lecture instead, you can comment in chat during the lecture or send me an email. Outside of that, it's fine either way. But definitely, if you have questions, let me know so we can address those. Finally, we will need a scientific calculator for this course. We'll be doing some graphing too, so the hope is that you do not have a graphing calculator. It's harder for me to enforce when I'm not actually watching y'all take the test, so you can anticipate the questions being asked in a way that don't strictly rely on the graphing, but more on the analysis of the graph, if that makes sense. Anyway, so that's our first part of our syllabus. That's the same thing I just clicked on. Sorry about that. This is just our basic syllabus for all Cal 2 courses. Didn't have any of the particulars that are relevant to what we do, but I do recommend that you read this. We're using for our text Larson and Edwards Calculus with the Early Transcendental Functions, 7th edition. And there's the different ISBNs if you need those. But yeah, read through that and make sure you're familiar with all the college policies that we include there, and so on. So yeah, we're going to cover Chapter 7, Chapter 8, Chapter 9, and Chapter 10. So yeah, we should expect to have a test on each of those chapters, basically, and then also the final. Now, let's see, what I might do for Chapter 7 is I might split the test into two parts, where it's part online and part work on your own, and just have you submit your work by a certain deadline. Some of those questions I want you to have a little more time to work on, although, yeah, I might do that. But yeah, then just a formal test for Chapter 8 and 9. I mean, we won't necessarily cover every section in Chapter 10, but I'll probably hit a lot of these. So, kind of depends where we are time-wise after we finish Chapter 9. That's part of it, actually. Anyway, so make sure you read through that. And the other thing that we have is, and this is what we're required to include from the college, is the Covet Statement, which really it doesn't affect us because it's really a statement about classes that are meeting in person that may suddenly be moved online depending on how things go. Since we're already in an online class, it doesn't really affect us, but if you have other classes that do meet like face to face, then that might be something to keep in mind. So I hope nothing happens there that requires it to, like in-person classes, be suddenly moved online, but we never know right now. So anyway, so make sure you familiarize yourself with those. As far as what I keep track of in Canvas, I'll certainly make use of the files if there's any like formula sheets or necessary documents that I need to upload. Your grades, you'll certainly be able to check your grades here. Announcements, you've already seen me make one announcement. That's another way I'll stay in contact with all of you as a group. And then also quizzes, when it comes time to take a test, it would be set up as a quiz in Canvas. So, do y'all have any questions? Are most of y'all using laptops or phones to connect? I was just curious what everyone's using. But I've seen from my other classes, most students are on laptops with a few on phones and a few on desktops. Yeah. How's the experience on phone? Are you all able to do everything okay? Yeah. Well, hopefully the experience is fine regardless of whatever you're using. Um, if you feel like I'm not writing large enough on the paper here, let me know, um, and then I can write either larger, or I can actually lower the camera closer to the paper. That'll probably work better, honestly. All right. I thought today we would start out with a little bit of review. I think that's a good place to start. Make sure we're all caught up. So obviously obviously all of y'all have completed Calculus 1, otherwise you wouldn't be in this class. Probably most of you took it in the spring, maybe some of you in the summer. But we just want to make sure, not to jump right into things. Let's try to make sure we're all caught up again before we move forward. Just to make sure we're in a good place as far as how we understand things. The biggest challenge for me here is making sure that what I write doesn't go outside the boundaries of the picture. So now, the majority of what we work with in Calculus 2, a lot of what we work with, especially like the first two chapters, 7 and 8, is on integration techniques and applications of integration. So in order for us to do these successfully, we really need to have a good grasp of the integration, as it turns out. So what I really want to review is kind of all the integration that we should have done up to this point. So specifically, this is a review of integration. So first of all, let's look at the kind of the things that we already know how to integrate. Certainly we know that the integral of x to the n, this is our power rule for integration. And we know that will be x to the n plus 1 over n plus 1 plus c. But we do know that this is only true for n not equal to 1, a negative 1 specifically. Okay, so whatever the exponent is here, we add 1 to that exponent, and then we divide by that same number. And then we, of course, have our constant integration that we want to include. What happens if we have the integral of x to the negative 1? Does anyone remember what that integral is? Okay, well, x to the negative 1 is the same thing as saying 1 over x, that's the reciprocal of x. And the integral of 1 over x dx, or dx over x, this will be natural log of x plus c. So in the case where n is not negative 1, we use the power rule, but if n is negative 1, it becomes natural log of x. The reason the power rule doesn't work is because if this is negative 1, we add 1 to that, to get x to the 0 divided by 0, which doesn't exist. Anyway, so we have that. That's for when we have x raised to a power. There's a few other things that, like specific things that we've learned how to integrate beyond that. We know the integral of sine x is negative cosine x dx, or sorry, plus c. We know the integral of cosine x is sine x plus c. We know, and we can do the other basic trig integrals. That would be the integral of secant squared x is tangent x. We know the integral of cosecant squared x is negative cotangent x plus c. The integral of secant x times tangent x is secant x plus c, and the integral of cosecant x cotangent x is negative cosecant x plus c. Now, these are based on the derivatives of the 6 basic trig functions. We know the derivative of sine is cosine, the derivative of cosine is negative sine, derivative of tangent is secant squared, derivative of cotangent is negative cosecant squared, and so on. So we've just kind of reversed those to set up these integration formulas. The biggest thing that I've seen students have trouble with is when is it going to be negative versus when is it going to be positive. And that's the big thing that we have to be comfortable with. We have to make sure we get the correct plus or minus sign on each of these integrals whenever we're working with trig specifically. So that is something in particular we should work on and strive to be successful at. Whenever we get a cofunction, whether it's cosine, cotangent, or cosecant, we know we have a sign change there. But if it's sine, tangent, or secant, then we don't have a sign change. That's one way that we can remember that. So cosine and cotangent and cosecant are all called cofunctions because they all start with co, and because of their relationship to the other functions, cosine to sine, cotangent to tangent, and cosecant to secant. This is one way we can help remember that, hopefully. The other thing I like to tell my students with sine and cosine specifically, because we may find ourselves taking multiple integrals or multiple derivatives in certain situations. So I like to give students this chart. So we have sine, cosine, negative cosine, and sine. If we go down the list, we're taking derivatives. Oops. And if we go up the list, we're taking integrals. Okay? So the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. And the derivative of negative cosine is sine. But if we go up the list, we're integrating. Integral of sine is negative cosine, which integrates from there to there, and so on. Okay. So we've basically looked at polynomials and trig functions, but there are a few other things that we've learned how to integrate. For instance, we know the integral of e to the x is... Well, what is the integral of e to the x? And you can just use the caret to show an exponent. Yeah, e to the x. Yeah, it's the only function. Well, actually, technically, there's another one. It's the only non-trivial function where it's its own derivative and its own integral to an extent. We want to be careful about saying it's its own interval because we can't forget the constant integration. But e to the x is the derivative of e to the x. The only thing that applies to, only other thing that applies to is 0, because technically the derivative of 0 is 0. But that's not as interesting because e to the x is a function that moves, whereas 0 means it doesn't do anything. So yeah, so we know that e to the integral of e to the x is e to the x plus c. Now, there's a few other special integrals that we may or may not remember. For instance, the integral of 1 over 1 plus x squared dx. That is arctangent x plus c. Also the integral of 1 over the square root of 1 minus x squared dx. That is arc sine x plus c, and the integral of 1 over x times the square root of x squared minus 1 dx is arcsecant of x plus c. Now those we're not going to be using quite as much. It's nice to be familiar with these. Like, if we can get to the point where we recognize we see these patterns, sum of squares or difference of squares under a radical on the bottom, if we can get to the point where we recognize, hey, this is something significant that we can use, that's good. It'd be nice to know these formulas, but I actually have a formula sheet that I will give you of certain integral and derivative formulas for like the more complicated things that we don't use as much. Things like the integral of secant, where it's like natural log of secant plus tangent, or the integral of hyperbolic cosine is hyperbolic sine, for instance. Those are the kind of things where it's nice to know. I'll actually give those to you on a formula sheet in case they ever come up, which more than likely they won't, but it's nice to have them just in case. But a lot of these things we're looking at here, I do hope that you already know because they won't be provided. I might go ahead and include these three on that list because they're a little bit more complicated than some of the other ones that we've looked at. All right. What else do we know already that might be the extent of it? Now, Now, beyond these basic forms, we still have the concept of substitution that we also looked at in Calculus 1. So let's look at that next. I can still use this page. Now, all of these formulas that we've looked at already, basically they can be used with substitution and to any extent. So, like if we have x to the n dx, we know it integrates x to the n plus 1 over n plus 1 plus c. Even if we change x to a u, the same principle still applies. Okay? So, if we say, for example, we have the integral of 2x plus 1 to the third dx, we know that if we spend enough time, we could actually cube that polynomial, multiply it out, and then integrate using just nice power rules. But that takes a lot of time, and it gives us a really, I think the answer is a little more complicated in that sense, because here we'll be able to still be able to write the answer as one term, which I think is nice. And what we have to do is, because we recognize, we have an expression to a power, and more importantly a linear expression where its derivative is just a constant, we can do a u substitution here. We can let u equal 2x plus 1. We also have to find its derivative. Derivative here is 2. Now, we know this will be our u right here. 3 will stay the same. But we don't have this 2 anywhere in this expression. So what we can do instead is we can go ahead and say that since du equals 2 times dx, we can just bring that 2 over and say du divided by 2 is equal to dx, and we can replace dx with this expression. So we can say now, after subbing everything in, we have u to the third times du over 2. Now the 2 that's in the denominator, we can just factor that outside, so it's 1/2. So we really just have the integral of u cubed. Now, for u cubed, we know this a power rule because we just have a single variable raised to a number. And the number is not -1, so we know it's not natural log. And then we just complete our integration from there. So u to the third becomes u to the fourth over 4. And so that's going to give us 1/8. If we multiply the 2 and the 4 together, that means 8 times u, which is 2x plus 1 to the fourth plus c. And that would be our integral in this case for that original expression. Now, we could write this as a single fraction if we want, 2x plus 1 to the fourth all over 8, or we can write the 1/8 as a separate fraction multiplying in front. I'm pretty flexible as far as what that's going to end up being, so don't worry about that too much. Yeah, so that's one form of substitution that we see. Let's look at another example. Move back up here. Now, Yeah, let's look at this. So if we have one integral of 1 over 3x minus 2 dx, it's actually pretty similar to that last problem, because technically we could think of this as 3x minus 2 in parentheses raised to the negative 1 power. But this is probably more like how we would end up seeing it, actually. Now, once again, we can change this expression on the bottom to be u. And then we have to take its derivative, which is 3. And again, we want to solve for dx to figure out what we have to substitute in here. So we'll divide this 3 over. Du over 3 can replace dx. And so we'll take all that and plug that in, so we get the integral of 1 over u times du over 3, or simply 1/3 times 1 over u du. What is the integral of 1 over u du? Yes, natural log of u. So we'll end up with 1/3 natural log of u plus c. Now, technically we should put absolute value bars around u. I'm not going to strictly enforce that, but specifically that's probably something that you would see in a very specific format. But yeah, we'll say 1/3 natural log of 3x minus 2 once we replace the u. Let's see, and that would be our answer then. Okay. Now, when we're working with exponentials, there's a couple of different ways that we see the substitution take place with exponentials involved. The first example I would like to do is, again, a relatively simple one. And for example, let's use integral of e to the 5x plus 1 dx. Now, again, we know that the integral of e to the x is e to the x. But that's also true if we have a u. The integral of e to the u is e to the u. X and u are basically the same thing. It's just a different letter, different variable system. But they mean the exact same thing. So if we can change this to be a u instead of 5x plus 1, that'll make it something we can integrate. E to the u integrates as e to the u. So we'll let u equal 5x plus 1. Take its derivative, that's just going to be a 5 dx. And again, solving for dx, we know du over 5 will replace dx. So we end up with the integral of e to the u times du over 5. Now, again, the 5 in the denominator, we just factor that out to the front, so it's 1/5 in front. And we just have integral e to the u, which we know is e to the u. Alright, and then from there, we just plug u back in, and that that is our answer, e to the 1/5 e to the 5x plus 1 plus c. Okay. Now I said there's multiple ways we use e to the x inside substitutions, or using substitutions to solve problems with e to the x built in. Let's look at another example which uses it in a different way. So the integral of e to the x times, in parentheses, e to the x plus 2 to the third power dx. Now we have two different things going on here. When we look at this, we might say, well, we could multiply it out, and that's absolutely a strategy we could use, but again, it would take a lot of time to do that. And we'd still have there'd be pieces of that that would be a little bit more complicated, so we have to be careful. It's actually better if we work with it in this form anyway. But the key to using u substitution is that in the problem we need to be able to recognize where our u is and then where its derivative is. Now, in our other two problems that we just did, I can pick this page up again. In these two problems that we worked already, and again on the other page, all our substitution was for this linear expression. Like we did 3x plus 2 here, and we did 5x plus 1 here. When we're substituting for just an ax plus b, a linear expression, the derivative is always a constant. So even though we don't see that derivative of 3x plus 2 present in this integral to begin with, because it's just a constant, we can easily factor it outside the integral and deal with it that way. The same thing is true down here. Our u is 5x plus 1, so its derivative was just 5. And even though there's not a 5 here, it's not a problem because we just put a 1/5 in there instead and factor it out. But what makes it more difficult and what we have to be more mindful of is this other situation I'm presenting you now, where we're not going to just substitute for a simple linear expression. Okay? Linear expressions are very easy to do substitutions for. It's when we have a nonlinear expression that it becomes more imperative that we pick the right thing to be our substitution. We have two terms here that are present. We have e to the x and we have e to the x plus 2. So we want to look at those and think about which one is a derivative of the other. Well, we already know that e to the x is the derivative of e to the x. So if we take this expression here, e to the x plus 2, I'll get your question in a second. If we look at this expression e to the x plus 2, it's the derivative of e to the x is e to the x, and the derivative of 2 is 0. So we can say if u is equal to e to the x plus 2, and then take the derivative of that, we get the e to the x, and then nothing from the 2. So it's just e to the x dx. Okay. When we say linear versus nonlinear, and I'll kind of do that over here. Linear, if you recall, means basically y equals mx plus b. And linear is great because the derivative, y prime, is just whatever the slope is. So in that case, it's no big deal because derivative is basically an expression for the slope. Now, for a linear line, the derivative is the slope, but for a nonlinear curve, then the derivative is now no longer just a single value, it's a changing value. Okay, so nonlinear is basically anything else beyond that. To put it as simple as possible, most of what we work with is nonlinear, but we frequently see these linear substitutions in U substitution problems, which makes them pretty straightforward. So. But yeah, when we have a nonlinear substitution, like in this case where u is e to the x plus 2, we have to make sure its derivative is present in the problem, because this time the derivative contains an x. When we had the linear terms, we can create a constant where we need to, because we can easily factor it out of the expression when we work with integrals. We cannot create a variable, however. If we have a variable in that derivative, that variable term has to already be present in the integral. Okay, in order for us to successfully make this substitution, this e to the x that we need for du has to be there already. It can't be something that we introduce ourselves. Okay, we can add, or we can multiply and divide by constants as necessary, as we saw on the other page. Okay, we let u equal 3x minus 2 here, and our derivative was 3. Well, even though there wasn't an extra 3 outside of this term, that's okay, because we know dx can be replaced by du over 3. We'll just factor it outside. What we cannot do, we cannot say dx is du over e to the x and take an e to the x that we introduced and put it outside the problem. We cannot factor anything with an x across this boundary. Okay? Because our integral is with respect to the variable x, x's have to stay in here, but constants can freely move across. Okay, cool. So that's really one thing we have to watch out for with our substitutions, that we're not overgeneralizing something or oversimplifying something where it becomes incorrect, basically. So in this case, we do our substitution. This e to the x plus 2 is u, so we'll call that u cubed. And then du is e to the x dx. That's all du. So essentially, we make our substitution here, and we have u cubed times du, which I've written as dx. I'm sorry. Okay, so that actually makes a relatively simple integration once we do our substitution. But this one, when we first look at it, doesn't look simple at all. And that's why substitution methods are really great, because it allows us to circumvent what might otherwise be a really difficult problem. So we integrate u cubed, and that gives us a 1/4 u to the 4th plus c. What happened to this e to the x? These two terms right here, e to the x dx, are part of du. Okay? So when we take our integral expression, everything that has an x in it has to be replaced with terms that have u. So we said u equals e to the x plus 2, so this expression here, in the parentheses, that's just our u raised to the third power now. And then the e to the x and the dx that are on the outside, those both are part of du now. So we have u to the third du. And that's where we get our result from. Okay. We needed this e to the x to be part of the du substitution. Cool. Good. Alright, and then u, once we get down here, we've completed our integration. We can now just replace u with e to the x plus 2 again. So it's 1/4 e to the x plus 2 to the 4th power plus c. Okay. Any questions there? All right. All right, let's look at let's look at some trig problems. That's not one of them. Sorry. Integral of sine of 4x plus 5 dx. Now, we know how to integrate sine x. We know the integral of sine x is negative cosine x. So that should tell us where we need to go with this problem. If we just had sine of x, or sine of a single variable, then we should be able to complete this integration. And that's our goal in each of these problems, complete the integration. We do sometimes have to take a middle step. That's where this substitution method comes in. Because we can't just integrate this like it is, because of the more complicated expression that is inside the parentheses here. Now, we look at this and, okay, we know integral of sine x is negative cosine x. So let's take whatever's in here, which is what's considered unusual in this problem. We have our sine function. We know how to deal with that. If it only had an x or u inside, we'd be good. So we'll let u equal 4x plus 5 du, that's just 4 dx. But again, 4, we could take and divide that over, so we can say du over 4 is equivalent to dx. So, looking at our integral, we end up with the integral of sine of 4x plus 5, that's u, times dx, which is now du over 4. It's really the same principle that we saw in the earlier problems. Okay, well, we know we can complete the integration there. It's 1/4 times integral of cosine u, which is negative cosine u. And this is where we have to be more careful with our trig problems. As I said before, more careful in making sure whether the answer is positive or negative. And that is a big impact if we get the wrong sign. So negative, and let me move that over slightly. Negative 1/4 cosine u plus c, and then we plug back in u, which is 4x plus 5 plus c. Now let's take the same problem and change it slightly. Let's say instead we want the integral of x times sine of x squared plus 5 dx. Now again, we have to be careful. Now, typically, like when we have trig functions, if we have a trig function that's not just x inside, but it's like an expression that's a little more involved, like x squared plus 5 in this case, what that usually tells us that this is the thing that's going to be our u substitution, the x squared plus 5 in this case. So if it's more than just sine x, the sign of a different expression than just x, whatever's in the parentheses we expect to be our u substitution. And that's the same for all of the trig functions. So we would expect u equals x squared plus 5 to be our u substitution here. Now the difference in this question is that we have an extra x on the outside. But then we notice if we let u equals x squared plus 5, we take the derivative of that and we get 2x dx. Now, we know that we already have x and dx here, but we have an extra 2. Now, the 2 we can go ahead and divide over and say, okay, du over 2 is x dx. But then beyond that, we'll be able to say, okay, x dx, that's just going to be du over 2. So we'll have sine of u times du over 2. Okay? So here's our u inside the parentheses. Sine stays the same. We haven't changed that. And then x times dx, we'll replace that with du over 2. Now we can go ahead and take the 2 on the bottom and factor it out. And honestly, if you feel comfortable enough, you don't even have to write the 2 here in the first place. You can just go ahead and put it on the outside. And so from there we integrate sine u, which is again negative cosine u. And we'll fill in the u value from there. Okay. So much like our last problem with the x times e to the x squared, it was e to the x times e to the x plus 2 or 3 raised to the power of 3. We can complete our substitution with that extra term that is in front of the other one because of the du portion. And so that's going to be the most helpful, is making sure we identify the correct u value and then making sure we take its derivative and properly substitute for the du as well, or dx in this case. Yeah, as far as grading goes, I will give you partial credit for if you don't have exactly the right answer. Now, something like that where you forgot to plug u back in at the end, I tend to grade like 10 points per problem. That would be like -1 point if you forgot that. It's not a huge portion. It's something I know you know how to do. It's just that you forgot to do it. So it's a very minor mistake, but I still need to take off something for that. But yeah, I'll certainly look at the work that you give me for those questions on the test and grade them with, if it's not completely correct, I'll certainly have partial credit available. Does that make sense? Cool. Yeah, I'm not going to I'm not going to take off like 5 points out of 10-point problem just for not resubstituting the u. That seems a little oppressive, but yeah, there has to be some little ding to the score in that situation. And even if you leave off the plus c, that's like -1 point. Okay, so it's a lot of different things that could happen. But certainly I'll take into consideration the work that you show me. Even if you didn't get absolutely the correct answer, as long as you're making progress to the solution, you're making correct steps, even if you haven't executed them correctly, certainly you'll get points for that. Because while it's great to be able to get the right answer, it's also important that we are using correct processes, we're making good choices as far as how to proceed with the problem. All of that goes into the scoring. Okay. Let's do some quick examples and see if we can see if there's a pattern emerging. So we're going to look at a function in the first column, and then we'll look at its integral in the second column. Okay, so cosine of 2x, if we integrate that, will be 1/2 sine of 2x plus c. And the point is that when we do that integration, we know that we're going to have to do a u substitution for 2x. And our du is going to be 2, and then we're going to end up with an extra 1/2 as a result. Integral of cosine of 2x plus 1, 1/2 sine of 2x plus 1 plus c. The derivative inside the parentheses, the derivative of our u, is still just 2, so we'll still end up with a 1/2. Cosine 3x, we'll get 1/3 sine of 3x plus c. Cosine of 3x minus 2, we'll end up with 1/3 sine of 3x minus 2 plus c. What do you think the integral of cosine of 4x would be then? One-fourth sine 4x plus c. Good. Yeah, and what we see happen is there's a pattern emerging. Like anytime we know that the integral of cosine is going to be sine, And as long as this is a linear term, 2x, 2x plus 1, 3x, 3x minus 2, etc., we know that the derivative of that part is just going to be divided on the outside. So if we have 2x, then we'll have a 1/2 sine 2x, 2x plus 1, 1/2 sine 2x plus 1, and so on. Now that doesn't just apply to like cosine, for instance. We could do it with sine. Okay. What about the integral of sine of 2x minus 5? What do you think that integral would be? And the goal here is really, for some problems like this, is to not have to actually go through the u substitution. We can just go directly from here to here as the integral. For these linear u substitutions, once you get a little practice, it's pretty easy to kind of skip past these and just go directly to the answer. Okay, and that's what it would be great. It would be good for us to be in that place where we can go directly from integral of cosine 2x to 1/2 sine 2x. Yeah, this is negative 1/2 cosine of 2x minus 5 plus c. The only thing different here is that we're integrating sine instead of integrating cosine. So the integral of sine we know is negative cosine, but again we're going to get a 1/2 because we have a 2 here, and then the expression here is the same inside. The point is that we see a pattern emerging, so that while we could do a u substitution if we feel like we need to, it's not strictly necessary for us to do that u substitution for this type of problem. Okay. So while we're thinking about that, what would you say the integral of e to the 5x minus 1 would be? It's really the same pattern that's happening here. Yeah, 1/5 e to the 5x minus 1 plus c. Because we have a u substitution for a linear term, 5x minus 1. So this, we know this will be our u. The derivative is 5, which means we're going to end up with a 1/5 in our substitution. And then we know the integral of e to a power is e to that power, generally speaking. So 1/5 e to the 5x minus 1 plus c. So the same thing applies to cosine, to sine, and to e. And if we can get comfortable doing those integrals very quickly in our heads, rather than having to go through the entire u substitution process, that's going to help us a ton in Calculus 2, because Calculus 2 is going to be much more than that. We're going to be using these same concepts, but then in addition to other concepts that we'll be learning. So if we can make these real easy, we can then focus on the complicated side of things, or not really complicated. We can focus on the other things that we need to be learning versus what we should have already learned. Okay, and I'm not saying you should have learned it this way, where it's something that we can recognize a pattern and then memorize, what it should be based on that. But it definitely helps us going forward if we can be comfortable with this concept. Yeah, a lot of it's pattern recognition, and I know that's something I was always real good at, so I don't necessarily expect everyone to be good at that right off, but if you can practice this, if you can study a little bit more and be comfortable with the patterns that we're seeing, then you can start to be able to skip those middle steps and go from the beginning right to the end. It makes it so much more easy as you go, because it's just less things to worry about as we're working through these problems. Now, this is, again, only if it's like a normal linear substitution: 2x, 2x minus 5, 3x plus 1, 5x minus 1. If that had a square on it, we couldn't do this. If we look back at this previous problem where we had x squared plus 5, we couldn't really take that same approach because we also had the extra x in front. So we're only talking about these in terms of just the basic function with a simple linear substitution that we would have to do. Okay. So it applies to cosine, to sine, to e. It actually applies to, let me show you another example. I'll flip the page over for this. It even applies in a case such as this one, where you might have secant 5x tangent 5x dx. Now we know the integral of secant tangent is secant, so what do you think this is going to turn out to be? Skipping that use substitution. One-fifth secant of 5x plus c. Right. This one probably seems a little bit stranger than the other ones we were looking at because we actually have two different trig functions here. Now, as long as they both have the same thing inside, well, we could say, if we wanted to, u is equal to 5x, du equals 5 dx. And we could go on from there and say, alright, we have integral of secant u, tangent u, and then du over 5, of course, from the dx. Okay. And so secant tangent, we know, is just the integral of that. It's just going to be secant, or hopefully we know. Maybe that's one thing we need to work on. Well, we look at this and we see how much work we've actually saved just going from there to there, just by recognizing that pattern. So I'm not saying you have to be perfect at this right off, but it's something I would like for you to work on as we go through these problems, and as you look back at this material. These situations where we just have that linear use substitution are so easy to take care of if we recognize the pattern. We can save ourselves a lot of work and a lot of effort. But it still goes back to recognizing those basic integral patterns, like integral of secant tangent is secant. The integral of cosecant cotangent is negative cosecant. I find that students are relatively comfortable with sine, cosine, and e to the x. Those are functions we work with quite a bit. These are a little bit less common, but that doesn't mean less important necessarily. These are still things that come up that we have to know, and that's where a lot of the challenge is, I think, for students is the kind of the less used aspects. When they show up again, they are sometimes confounding. So that's something that we just need to be mindful of as we keep going. What else do we need to say here? Do y'all have any questions? Okay. Now, cool. Normally at the end of class, I would give you a set of homework problems to work on. Today, since it's just review, I don't really. I'll give you a break today at least. But on Thursday, we're going to start chapter 7, and we'll do one or two sections from that first chapter. You may have noticed I didn't give you a schedule just yet, like for the semester or like a calendar. That's something I'll be working on. Hopefully by the end of the week, I'll have that ready and upload it to Canvas so you can look at it. I'm a little bit behind, so I'm sorry about that. That's in all my classes, not just this class. So, but I hope everyone's been doing all right, and I hope you all have a good rest of the afternoon and take care. And I will talk to you again on Thursday. You all have a good day.